Hey Mech Warriors, welcome to Bad Ben's Battletech. I'm Bad Ben, and this is episode 3 in our series of building a solar system according to campaign operations. Today we're picking up where we left off in the last episode, calculate gravity. This is what we're on. So it's this calculation here, which isn't too bad. All we have to do is we have to take the density, we have to divide that by 5.513, this number here, 5.513. Our density, if you remember, we took that for each planet. It's here. Then we're going to take this whole number, the result of this calculation, and we're going to multiply it by our diameter in this box, divided by 12,742. So that's the calculation. Get the calculator out. We have our density for the first planet is 6. We'll divide that by 5.5153. That equals that number, 1087, which is right here over in the side. I can see it. We need our diameter, which is 1300, divided by 12,742. And we take the result of this number, and we multiply it by that one, which was 1.08788. And that equals 0.11. So the gravity for our first planet will be 0.11. What did it say? 0.110. Yeah, so I don't need to round it. Move on to the second planet. Start with the density, 4. 4 divided by 5.5153 is 0.725. It will be saved over here. Then we have the diameter of our second planet, 1650. So diameter of a second planet, 16,500, not 1650. 16,500 divided by 12,742 equals 1.29, and we'll take that and we'll multiply that by the last calculation, which is, I still see over here, 0.725255. Oh, I didn't put a point. 0.725255 equals 0.93. That's the gravity for, wait, I got to round these numbers, 0.939. I'll put 0.94. 0.94. Terrestrial, it has a density of 6.3 and a diameter of 10,500. So we'll start with the density of 6.3. 6.3 divided by 5.5153 equals 1.14227. Our diameter was 10,500. 10,500 divided by 12,742 equals 0.82. Now we're going to multiply that by this calculation over here, which is 1.142276 to get a gravity of 0.941. Also 0.94. Wow, they have the exact same gravity essentially. This one is larger but less dense. This one is smaller but more dense. Asteroid belts, we don't need to do that. You could figure out the gravity of any small dwarfs within your asteroid belt if you've rolled for their diameter and density. I haven't. I don't want to. We'll move on to the gas giant, which has a diameter of 130,000 and a density of 1.5. So we'll start with the density. 1.5 divided by 5.5153 equals 0.2719. The diameter was 130,000. 130,000 divided by 12,742 equals this, and we'll multiply that by our last number over here, which is 0.271970, to give us a gravity of 2.774. I'll round that to 2.77. Empty space has no gravity. Ice giant, we have 55,000 for the diameter, 1.7 for the density. So we start with the density, 1.7 divided by 5.5153, 0.308. Diameter, 55,000. 55,000 divided by 12,742 equals 4.3, multiplied by the result of our last calculation, 0.308233. Forgot the point again. 0.308233. This number over here, and the answer is 1.33. So the gravity for this planet is 1.33. Our terrestrial has a diameter of 6,500 and a density of 3.5. So 3.5 divided by 5.5153 equals 0.634. The diameter was 6,500. 6,500 divided by 12,742 equals 0.51 multiplied by this number, which is 0.6345982. You probably don't need that many digits. 0.63 would probably be even fine. I'm just like that. Giving us a gravity of 0.323. 0.32. So that's our gravity. Gravity's figured out. Moving on. Calculate escape velocity. Terrestrials only. We really don't need to calculate the escape velocity for dwarf terrestrials. They can't have an atmosphere, and that's what this number is going to be used for. It's going to be used to make a escape velocity modifier for our planets, but only ones that could have atmosphere. So dwarf terrestrials, stay out of it. I won't do the dwarf terrestrial. The giant terrestrial could get atmosphere. It has a 1 in 6 chance of getting an atmosphere. But that doesn't come till later on, so we might as well calculate its escape velocity now. I'm probably going to just give it an atmosphere. I'll roll a 6 if I feel like it, just so that we can, it gives us more stuff to work with later on to fill out more charts. So the calculation for this one. The calculation for this one is very similar to the last one, but slightly different. If you're wondering what these numbers are, 5.5153 is the density of the Earth, and 12,742 is the diameter in kilometers of the Earth. So the last calculation that we did basically just gave us a relation of mass of this planet in relation to the Earth. And this one's using the same numbers because we're also going to get, we all sort of, I shouldn't talk about like I know what these calculations really mean, but we have the same numbers in them. So what we have is, again, density divided by 5.5153, but we're going to take the square root of that number and use that. And then we're going to multiply that by the diameter divided by 12,742, and we get a new number. And we take that number and we multiply it by 11,186, which I assume is the escape velocity of the Earth. And that will give us our escape velocity for each terrestrial planet, excluding dwarf. Well, you can do your dwarf terrestrial planets. You can do the escape velocity of any planet, but I keep stuff to a minimum of what I need to calculate, so I'm just simply not going to do that one. Giant terrestrial. And we will start with the density, which is 4. So the density of 4, same as last time, divided by 5.5153. And now we have to take the square root of that number. So 0.8516. Remember that. Now, what was the diameter? We have to take the diameter, 1,300, divided by 12,742 again. And then we multiply that by this number here, which was the square root of that number, 0.851619. Giving us this number, 0.008. Now we have to take this number. What we've done, we've done this. We've done this. We've multiplied those together. We did this including the square root. We did this, we multiplied those two numbers, and now we have to multiply our result by 11,186 meters per second. So multiply by 11,186 gives us an escape velocity of 971. Wow, 971.9. 971. No, I'll round that to 972. Don't need to put the points in there. It's not really important. Terrestrial, so we start with the density, 6.3. 6.3 divided by 5.5153 equals, take the square root of that number. Now, the diameter for our it was, sorry. I made a mistake, and I know what my mistake was. This, I thought, escape velocity at 972. I used the diameter of the dwarf terrestrial for that. So we're going to have to redo that one. Sorry, guys. Just going to start again from the beginning. So the density of that is 4. I knew there was something wrong. 4 divided by 5.5153 equals this number. We take the square root of that, 0.851. Good. Now we take the proper diameter, 16,500, divide by 12,742 equals 1.29. We multiply that by this number over here, 0.851619, giving us this number, and then we multiply that by 11186, giving us, that's much more realistic, 12,335.7. 12,336. That's the escape velocity for the giant terrestrial. That makes sense. Since they have the same gravity, will they have the same escape velocity? Probably not, because the radius makes a difference when you're trying to leave the planet. Let's see. So we start with 6.3. 6.3 divided by 5.5153 equals 1.14. Take the square root of that number, 1.06. Now, the diameter was 10,500. 10,500 divided by 12,742 equals that. We're going to multiply it by this number over here, the result of the last one, which is 1.06877. And we take this number and multiply that by 11186, giving us, no, it's not even close to the same escape velocity, 9851.6. I'll write 9852. 9852. Asteroid belt doesn't matter. No escape velocity. Gas giant we don't do. Empty, obviously, as well. Ice giant we don't do. Terrestrial, the last one. So we have a density of 3.5. We have a diameter of 6,500. Let's see. 3.5 divided by 5.5153 equals, take the square root of this number, that's it, 0.7966. The diameter, again, was 6,500. Divided by 12,742, and that equals that. And we'll multiply that by this number over here, 0.796616, giving us 0.40, and we'll multiply this by 11186, giving us 4,545.6. 4546 is what I'll write. 4546. Escape velocities are done. Moving on, calculate year length. Page 105. There are two year length calculations. This is the easier of the two. This is the one I like. If you want to do the other one, you're going to have to go and read how to do that yourself, because I'm not going to explain it. This is good enough for me. So this is our calculation here. Ty is the years, the time measured in Earth years that it takes the planet to go around the sun. Ra is going to be the radius of the planet, and we're going to cube that, okay? And we're going to divide that by the mass of the sun. We have the information for the mass of the sun right here. It is 0.8. All right. So we take the radius and we cube it. This is for year length. We take the radius of the first planet, 0.032. No, not 0.032, 0.32. And we cube that to the power of 3. That's what it said to do. Right here. We're going to take that and divide that by the mass. The mass, again, is recorded down here. Mine's 0.08. So our answer, we're going to divide it by the mass, 0.08. Right? So we've done this. And then we simply have to take the square root of that number. Take the square root, which gives us a time in years of 0.2. So for the dwarf terrestrial, all the way in the inside of the solar system, it has a year length of 0.2 years. That would only be a few months to go around the planet, the sun. So the next one, our radius is 0.56. We'll be using the same mass of the sun, 0.08. So we take 0.56 to the power of 3, giving us this. We divide that by 0.8, the mass of our sun, giving us this. And then we take the square root of that number, which gives us 0.468. I will write in 0.47. For a terrestrial, which has a distance of 0.8, I know the answer to this one already. 0.8, we'll do it anyways, to the power of 3, divided by our mass, 0.8, equals that, and we'll take the square root of that. No. I pressed the wrong button. It doesn't matter. It gives us the right answer. The answer is 0.8. So it takes 0.8 years for our terrestrial to go around the sun. For the asteroid belt, we can do it as well. That makes sense. How long does the whole asteroid belt take to go around one time? So our distance is going to be 1.28. 1.28 to the power of 3 gives us this. Divide that by 0.8, giving us this, and we simply take the square root, which is 0.474. So I will write 0.47. I did something wrong, didn't I? How can that be the same as this one? Try again. 1.28. 1.28 to the power of 3. That equals this number. Then we divide that by 0.8, the mass of the sun, in relation to our sun, which gives us this number, and then we take the square root of that. Much better, 1.61. I'll just write in 1.6. For the gas giant, we have the distance of 2.24. So we take 2.24 to the power of 3, giving us this, divided by 0.8, giving us this. Take the square root of that, and we have 3.74. I will simply write in 3.7 years for the gas giant to go around the sun. Empty, we could calculate, but that makes no sense really. We know the distance of empty space. Next one is the ice giant, 8. So we simply take 8 to the power of 3 divided by the mass of our sun in relation to our sun gives us this number, and we take the square root of that, and we get 25.29. Takes 25.3 years to go around our sun. That seems like a big gap from this one, but if we'd calculated empty space, it would be somewhere in between. And they take big jumps as you get further away. So our last planet here, 15.68. 15.68 is the distance. Cube it. All right. Divide it by 0.8. The mass of the sun in relation to our sun, and then we take the square root, which gives us 69.4 years. 69.4 years. Years are finished. Year length. Calculate escape velocity modifier for terrestrials only. So this is only for planets that might have an atmosphere. So the dwarf terrestrial, we're not going to do it for this one. We're going to just forget about the dwarf terrestrial. For the giant terrestrial, we will calculate it. For the terrestrial, we'll calculate it. And for this terrestrial, we'll also calculate it. And this information is actually going to be recorded down here. I'm going to assume that this giant terrestrial is not going to be habitable, and it will be recorded over in this field here along with the terrestrial out here. The terrestrial which I will make habitable, I will put its escape velocity modifier here. So we'll start with the giant terrestrial. Escape velocity modifier, we'll have a look at it. It's very simple. You take the escape velocity, divide it by 11186, and that's your modifier. Easy as that. So escape velocity of the giant terrestrial, 12,336. 12,336 divided by 11186 equals 1.1. So I'm going to come over to this table here. We're recording for the giant terrestrial, which is in orbital slot 2. We can already put its if it happens that it will become habitable, I will move this over to the other table. Whoops. Oh no. What was it again? 1.1 is the modifier. That's not going to make any difference to our rolls, I don't think. But we'll see. Oh, it could make a difference if we roll high, I think. So moving on, we have our terrestrial planet here in slot 3, which I will make sure is going to be in it's going to be habitable, so I'm just going to put it in the habitable field here. And we want its escape velocity. So the escape velocity for that, I went by it, 9852. So we simply take 9852 divided by 11186, and that gives us 0.88. And that's modifier is going to be 0.88. I'll put 0.88. That's fine. All right, the only other one that might have an atmosphere for us to worry about is going to be this terrestrial down here, who has an escape velocity of 4546. So we simply take 4546 divided by 11186. That gives us 0.4. I'm going to record that in this field here, 0.4. That is in orbital slot 8. And is a terrestrial. So those are all of the escape velocity modifiers. Calculate ear length. We've done this one. We move on to number 14. Roll for atmospheric pressure. Roll for atmospheric pressure actually brings us to the end of this video. The rest of it will be done in the last video. We will do from here, roll for atmospheric pressure, down, and fill out the rest of our fields. So thanks for watching. I hope it made sense. I hope I didn't make any mistakes. If I made some mistakes, please forgive me. I'll simply live with my mistakes. And that's fine. Anyways, thanks for joining me. Hope to see you in the next video. Bye-bye.